Right. Let's get started. It's my great pleasure to introduce Dr. Xiali from University of Louisiana at Lafayette, and she is a Alfred and Helen M. Lamson Endowed Associate Professor in the School of Computing and Informatics, and she was assistant professor there, and she was awarded with multiple awards such as an Outstanding Achievement Award in External Funded Research, an NSF Track 4 Faculty Fellowship, and NSF Statistics Small Award, NSF MR Award, Meta Award, and NSF CRR Award, and also like CEMC Talent Initiative Fund. She also received like awards such as EAI Smart SP 2023 Best Paper Award, ACM 2014 Mobicom Best Post Runner App, and Dissertation Completion Fellowship, and also the several student grant from IEEE Infocom and IEEE Globalcom. And she earned an MS in software engineering from Tsinghua University, and also a electrical engineering from Xi'an Jiaotong University. So let's welcome Dr. Hey.
Thank you very much for this introduction. Thank you very much for inviting me here. My name is Sharon, so it's my great honor to be here. So today I'll talk about how to investigate and mitigate the attack caused by the out of the binary signal. So I will mainly give this. So I have secured more than 24 million funds and PI more than 3 million at my personal shares. I also published a lot of papers. So I'm dedicated to my computer work. You see, once I get an opportunity, I usually invest and succeed. So for my NSF CRI work, I got the first try. For my NSF up to 224, I also got the first try. So I got the MRI second try. I got my CSE small work first try. So NSF, up to the tech, first try. Yeah. So people think I'm a go-getter, but I know there are a lot of intensive efforts in each achievement. So I usually spend more than 120 hours on each proposal. Yeah, I think the high research quality is the key to success. So I also mentored several good PhD. So we see this first one is Yazo. He right now is in the Auburn University. Yeah, he have a lot of top tier security paper. Yeah, that's the thing. So here is some of the work we have done in the security. Most of them are directly on the hardware level. We also have all of them have demos and videos. So we work on the both attack side and the defense side. We also have the side channel analysis. So besides, we have one IEEE security and privacy 2024 paper and review. So that's why it's about how to fully control Tesla car using the EMI attack. Because the disclosed problems, I cannot share that with you right now. Yes. So today I just briefed 6 papers. So this is the other papers, conducted by for the machine learning for the security and AI model security. We have a subtitle here, AI model security. We also have one useful paper and a review. That's why it's about how to bypass the filter in the large language model by the jargon. Yeah. So that one also not included here. Okay. So today I need to focus on the CPS, our CPS work. Okay. So why do I think the CPS system security is exciting? Because these days there are so many investments, in the CPS, in IoT system. So if you take a look, you can see the sensors are everywhere. So that's why we want to, secure such applications, to secure such, systems. So all these systems have to do with the physical world. So and their decision making includes the autonomous and AI powered system. We heavily rely on the sensor output. So if there's some error, if there's some attack under there, this means so the decision system may give the unexpected response. So this one may put the passengers, the drivers, and the patients in the danger. So that's why we want to, invest our time in this area. Okay, so the main insight of our research is that the security and the safety of the CPS require the threat model and computational resistance to the complex physical world. Okay, so how to make the next, the CPS system secure and trustworthy. So we talk about two research questions here. One is how to anticipate the analog domain in the sensing risks in the sensing. Another one is how to design and control the computations to analysis and manage the security, privacy, and safety risks. So this is the outline of today's talk. So in the first part, I will focus on the acoustic, on MU sensors. Then the next part, we talk about the defense. Then we talk about the EMI attacks on the sensors. So in the first part, I'll brief 3 papers. The first paper is our useness papers. So this one is about how to use acoustic signal to control the CPS system. The second one is our CPS LT-SEC paper. This is one more advanced paper. So this one is doing the automatic attack to control the actuation of the target. So previous paper, you need a manual, the adjusting, but here we totally don't need any, the manual work. Then the third paper is the Smart SP 2023 paper. So this paper is about how to, detect and mitigate the attacks in the first 2 papers. So there are a lot of, the immersion sensors, but 2 of them are very important. One is gyroscope, one is accelerometer. So they can be used in many applications, where the system makes decisions based on the motion feedback. So in 2007, there is a research group found that MEMS energy sensor is vulnerable to the resonant frequencies. So resonance is a physical effect. So you see, if we want to break the glass, you can see with a specific note that note is on a resonant frequency. It's also called the natural frequency. Okay, so we found that the problem is right now the sensor become very, very tiny and light. So the sound of the energy of the sound can do significant radiation of the sensor. Okay, so we found that it is vulnerable to the acoustic resonance. In the 2015, so there is a paper called the DOS attack on the gyroscopes. So they use such effect to crush the drones. But what they do is a DOS attack. So DOS attack means they just mess up the reading. They cannot, control the reading of the sensor. But then later on, there is a research group from the Dr. Kevin's group. They can control the accelerometer, but they only control less than 2 seconds. So they also require the access to the internal data because they use a white box approach. Okay, so that's the previous, their work. So they use the white box approach. So in this approach, they know the internal setting. They know the data come back. If they don't, they cannot monitor the data. They cannot, conduct the attack. Okay. So, however, in the view setting, if you want to really control the immersion sensor, so you cannot control the internal setting. Also, you don't have the view time data. So you only can observe what happened in the system, only observe the behaviors. Also, there have the sampling rate drift. So when sampling rate drift, so the previous work they cannot hold. So that's why their attack only success less than 2 seconds. Okay, so we want to investigate how to do the black box approach, how to control the MU sensor of the victim system as long as we want. Okay, also we can adjust, the attack. So to better understand the problem, let's take a look at how the acoustic attack can induce a specific signal in the sensor output. With the resonance, so attack can induce analog signal by playing the sound waves at a frequency, F. So that's an attack, signal, attack signal, their frequencies. Okay, so the sampling rate of the ADC is Fs. If there is no attack, they can, work normal. However, when there's attack, so the anything happen. So here you will see a very high large, the very high frequency F, they usually 20K, above 20K hertz, 27 something, ultrasonic. Okay, then after anything, so they become a very low frequency. That's the emission. Okay. So when the emission equals to 0, so that's a DC signal. That's a previous paper. They need this. However, we found that the Fs always drifting. Even very, very small is 1/7, drifting. Also make previous work cannot work. Okay, so the drift could be amplified by the n times. From this equation, you can see that anything, very tiny one could be, amplified. So that's why, previous work cannot work. So we produced, come up 2 attack. One is called set switch attack, another one is automatic attack. So from the DOS attack, previous one, you can see there's, movement of the sensor because it's oscillating. You see, because it's natural. The sound, sometimes bigger, small, it's oscillating signal. That's the physics of the sound. So what they do? So they have to make the system, turn to one direction, okay, turn to one direction, then go back in another direction. So they cannot control the sensor as well because you see the cumulative height angle. It's always 0. It's always 0. Okay. Then we come up. So the theta is fluctuate, cannot be controlled. Okay. So we come up with set swing attack. So that means when it goes positive, it turn left, we increase amplitude. When they go another way, turn right, we decrease the amplitude. Then we can control the, the sensor output. So we can control the sensor output. That means we can direct the sensor, the zoom, go to a specific place. Okay. So that's the set swing attack. That's what we found. So we all have a switching attack. So for the switching attack, you can see this one move left, this one, it should be go to right, okay, naturally, because that vibration go, one direction go to another one. That's a sound wave. That's a sound wave of physics. Then we make it, not go to right, go to left again. So go to left again, go to left again, left again. So we can control it. That's how to do that. So how to do that? We have 2, attack signal. One is F1, another one is F2. That's 2 frequencies. Okay, to do this, take a look at that. So we can control the heading angle of the sensor. So we can go to the specific place we want. Okay, so what we do, we switch frequency from the F1 and F2 back and forth. Then the basic idea is we want to induce the positive and the negative frequency in the acoustic attack. Okay, so this is the attack on the closed loop and open loop control system. We tried on the you see self-balance transporter, robot, camera stabilization, screwdriver, VR headset, and 3D mouse and a smartphone. We tried all of them. Most of them that works. Okay. So however, in this part, you take a look at that. So that's the menu. Use the hand to to do the work. You see, this is a target direction. We can control it to the target direction because if usually it's go back and, the forward. Also, if there are no tag, it should be stationary because nobody do anything on that. It should be stationary. But when we play sound, so the movement of the, the screwdriver, scooter could be controlled. Okay. So there are no sound here. Little bit. Yes. So let's take a look at how to do the automatic tag. Previous one is use the manual, handling, but then now we don't use the manual handling. Okay. So hand tuning is very slow, rely on the humans, reaction. So we write a code, to generate a sound by itself, adjust itself, to control the sensor. Okay, so this is the one, as I said before, we need to have a negative, frequency, and we need to have a positive frequency. So we have one example here. So the NFS is 20. So F1 is 1 hertz less line, F2 is 1 hertz above it. So we can continually change their movement direction. So you will see we control the iPhone. Take a look at that. You see this is positive. That's the red line. The red line is always above 0. Even you move the phone, maybe you do some other thing, it's still above 0. Above 0. That's what we control. We also control the Google Map and the VR game. So previous one, you need to collect your you need access the sensor data. Okay, but here we don't access sensor data. We just do the remote. We know nothing. This one also a black box approach, automatic tag, nothing. So this was much more advanced attack. Okay, so the main problem here is because previously we need just a signal, switching attack and the set switch attack. You need just a tag signal. So how to do that? So you need to know when to adjust that. Okay, so the time selection is very important. If you don't have any, the information come back, don't have any data come back, so how you do that? So we estimate that. You see that we have the, if we just look around the screwdriver wheel, if it goes to the, clockwise, we think it's positive. If it goes to the counterclockwise, we think it's negative. It's negative. So you'll see the speed, this speed up first. Then when they go back, the speed becomes close to 0. Okay, so that's the point we monitor. So how to use this automatic attack with the physical domain attacks? So we build an adversary control loop. So use the physical feedback side channel. So from here you can see there are some points, the speed close to 0. So we use our code program to monitor this, in real time. So first we play the sound to the, the sensor. Then, we monitor the actuation of the system. Then we do the calculation. Then we adjust the signal, tag signal. So they continuously, can control the CPS system. So 3 of these programs runs in the parallel. So they do in the real time. So this is the general procedure and the basic module for the user algorithm. It is a multi-thread program to form the continuous real-time control. Yes. So you see this one code is run in the Raspberry Pi. So we use Linux Arduino API to generate the sound. Then, with a very low frequency, the program has multi-threads to make all the modules together. So in this way, we can control the algorithm, running to manipulate the CPS, the behavior non-invasively, automatically, and any long time. Okay, not previous paper is only that's 2 seconds. This one any long time. Okay, so from here you can see in the first, the 20 seconds. So the move direction of the, they have different left, right, they have a different one. But when we start the attack in the 90 seconds, it just like give commands to the system, CPS system. So they just move to one direction. You see, all of them move to one direction. So this is the exact data from our program. Okay. So this is the one. Let's take a look. This one. So in this demo, we want to make the motor. Oh, you can see it. Okay. Of the scooter rotate in the counterclockwise direction. So we use a 3D printer, parabolic microphone to capture acoustic signal from the motor. So this is the mic. Okay. So this is the code we use. This is the scooter. Okay. So this is our Raspberry Pi. We connect to all the system. Okay. So attack program runs in the Raspberry Pi to extract the feature, just attack signal, will come to the scooter at the same time. Here, you see the camera screen here. They just want to show the data. Just want to show data. There's nothing. Everything is on. So if there are no tag, it should be stationary, no moving. Okay. So another tag, so we can make it move to one direction at any longer time. We want to give more challenge, so we put a very big, loud of the phone, give more noise. But we found that they robust to the noise, robust to noise. If there is noise, it still work. The noise is very, very loud, but this still work. Okay, so this is our attack. So we want to highlight our attack on the embedded inertial system. They can control system with actuator in the view tab. If attack is not connected to any digital surface of the system. So this means if all the data is encrypted, if all the data is wireless, we still can control the CPS system. That's something we want to highlight. Okay. So in this part, I mainly focus on how to defend against acoustic signal in the inertial sensors. So I would like to talk about how to use the multiple ADCs to detect out-of-band signal injection attack. It is joint work with my collaborators in the UPenn and the University of Florida, and Dr. Lin from Ohio. Okay, so before I start, I want to give a little brief of the current situation. So people think, inertial sensor, I can use the low-pass filter, all of them. Actually, not work. Okay, and now people are still saying we use shielding. But if you use shielding, because the sensor very tiny, like your finger sling, very tiny. If you use shielding, so their temperature will increase. There's the size, there's the cost, their usability, they have problem. Then people think they'll have a sampling-based method, like random sampling, or cancel the frequency. But actually, this one also not work. Because their attack frequency is not one, properly is many. If you shield, if you cancel one, you cannot cancel others. You cannot cancel that. If you use random sampling, so they lower the accuracy. Okay. So in other words, all of that, cannot detect, cannot correct attack, effects. So our work, we also can find the possible, attack frequency. We can mitigate that, can remove that. So this is the high-level idea. We use the component redundancy in one sensor. It's not the sensor fusion. So the ADC's sampling frequency need to satisfy a condition. The condition is pairwise relative, prime. So also all the ADCs work together, So then we do the analysis to find the declared attack, then correct the induce the wrong signal. Okay, because some ADCs have the multiple paths, so the sampling rates could be easily set, easily integrate, Also, they have less error than the field. So it's, convenient and economic to use the ADC's multipass. I have talked to the industry, about this. Sometimes the ADC's multipass, they also can work. Just use one ADC. Yeah, not use too much ADCs. Okay, so here you can see this is our system model. You see the attack signal and the normal signal come together. I have the multiple sampling rate. Then we do the system analysis. So we get the original signal and the original signal. We separate that up. So based on this equation, you will see we have a different sampling rate here. So if there's no attack, so we only have one frequency. We will have the signal, the output signal is one frequency. And if we have several attacks, you see the frequency different, then the emission will be different. So we will see have multiple, frequencies in the FFT domain, in the frequency domain. So we see if there are no attack, so then have only one overlap peak. If they have attack, so they have multiple separate peaks. So that's the basic idea. So based on this, we can detect the attack. Then let's take a look at how to reduce the attack. Okay, so according to the peak frequency we get from the previous, the figure. So we can do the calculation. So how to do the calculation? We based on this. So I give one example. If the sampling rate is 250 Hz, so this is the possible attack frequency. If the sampling rate is 90, 120 Hz, this is possible attack frequency. Then we see the overlap of that. Okay. If we have another one, so they have the matching, the narrow, possible attacking frequency. So that's why, if we know the possible attacking frequency, then we can remove that. That's how we do the detection. So for this method, so for the adaptive attack, they cannot work. Also, if the frequency have some more constraints, you can increase the number of the ADCs. Okay. For the frequency hopping and the frequency sweeping, they also cannot work. So that's the advantage of this method. So we proposed a component redundancy scheme to detect the acoustic out-of-band signal. Also, we can mitigate them. So we integrate how to find the real physical signal from different result from the redundancy component. We also deploy this method in the the commercial ADCs to evaluate our method. Okay. We also discuss how our strategy could be used in the future, sensors design and manufacture. So that's in the paper. Okay. So any problems so far? This is about the ADC's attack. The next part, I will move on our EMI attack. No question.
To have one question. So in some cases, there may be multiple sensors that are monitoring the same system. So like if you attack the sensor, the other sensor may also be attacked. So if you want to control the sensors, like maybe different sensors have different, like for example, speed and different directions. So how would I achieve?
Yes. So if for the EMI, for the inertial sensor, you need to use different kind of the attack frequency. Okay, that's have problem. But for EMI, later I talk about, they can attack, several sensors act together. So that's why the sensor field will not work. So all the sensors will be attacked. Okay, they use a specific, the frequency. Okay, so the locality is very good. We notice this situation, because the EM, especially the inertial sensor from different maker, different manufacturer, their frequency, attack frequency is different. It's different. Yeah. You cannot use one frequency for all unless they are overlapped. But some sensors, they have multiple attack frequencies, as I said before. if you know the three sensors have the overlapping of the natural frequency, you can do that. If they don't have overlapping of the technical frequency, natural frequency, you cannot do that. You cannot use sound to crush multiple sensors together. Yeah, but for EMI, you can do that. EMI, we use EMI signal can crush several, the can attack several sensors at the same time. So that's why for the sensor fusion, they probably cannot work. So today, I'll talk about the EMI text. Okay, this part is 3 papers. We have the ACM CCS paper. We have this ACM Cycle paper. We have ACM CCS paper. All of that goes to ACM. Yeah. Okay, so this is journal work with Dr. in the university on the Michigan at the same time. Okay, so this one we want to let you know even the shielded temperature sensor could be manipulated by the EMI signal remotely. Also, there are no any alert. There's no any alarming to you. Okay, so that's the no any error message to you. So that's why it's very concerning. Okay, so this is this paper. So can the temperature sensor data be easily manipulated? The answer is yes. So you see that we use antenna to try to affect the temperature sensor. You see the data come out is below the absolute zero. It's non-existent temperature. So people think, oh, I don't have antenna. How to do that? You just use a walkie-talkie. Very easy to do that. So what can an attacker do to control this? So you see this before the attack, it is 26 Celsius degree. But after the attack starts, so we can control the temperature as we want. Okay. So this part also, so you can modulate the system data. So this one when we use a shielded thermocouple. People think I already shielded, so it should be not vulnerable to EMI, but actually it's not. Actually, it's not. Okay. So the power only used, you see that's a 3 watt power. The distance 1 meter away. Okay. Since the EMI can penetrate the wall, sometimes your device is here. We just do attack outside of the door. Okay. Maybe it's in the neighbor's room. Maybe it's on the different floor, on the different floors. You can do that. Yeah. So the real world, the effects could be very severe because temperature system, they may affect you see medical device, vaccine, and the biomedical applications. I want to give one example. So this is an attack on the edges of the room. Okay, you see we have the incubator here. Attack is in another room, so we cannot see that. Okay, so the wall is 15 centimeter. Okay, we can make the incubator do the cooling attack and the heating attack. So we can make them just a cooling down and a heating down system without any alert, because their alert, if you be below 37.5 Celsius, they have alert. If you above that, if you really below 36, they have alert. But actually, we can really launch that attack for a long time, but not taking any alert. That means we can control that. Okay, another interesting result is we can use the frequency of the 400 megahertz, so we can disconnect the 3D H2 with a different frequency. That's 1 gigahertz, so we can make the temperature wrong. So the temperature is 23 Celsius, but with our tag, it becomes 33 Celsius. Okay. So you see the real concerning part, because system just heat up and cooling down and EMI injection without any reporting, any message. Yeah. Okay. So this is this one. Then let's take a look at our Sato 2023 paper. So the message of this paper is the EMI on the brain control interface device can change the machine learning results. Okay, so you see this is the first paper on the security of the EEG-based system under the physical signal injection. So the EEG data is widely used in the health care, in the research, in the internet. Okay? So especially if they have some headset, they use EEG signal, brain control signal, they have that. Okay. So here is a simple overview of the EEG-based intelligence system. So the essential component involved processing and analyzing the EEG data include the data acquisition, the pre-processing, and the feature extraction and classification applications. Also, they use the machine learning and deep learning technology try to do the precise classification. Okay, so let's shift our attention to the security of such system and analog domain attack. Okay, so with much attention has been given to the data threat and cyberattacks, the vulnerability arising from analog signal injection in this system. This part is not being explored yet, so that's why we are the first paper on this. So the objective of this system is trying to access the security and availability of the brain control system. Okay, so the consequence could be severe. So attack can lead to the misclassification of the EEG signal, resulting in incorrect diagnosis and the interpretation. Also, the manipulation of the results could give you the incorrect treatment or action to the patient. So this is the first demonstration of the physical signal injection with the machine learning and deep learning using the EEG data. Our technology, this non-invasive attack, we just injected it to the EEG brain control system. So you can see the later you can see the picture. So we really can manipulate the machine learning results. So for the simple pattern, like the sine wave and the square wave, the injected signal is very easily filled out. So we are not concerned about that because the field can work. However, for the brain wave component, they are the theta, alpha, and mu, brain bundle wave. This one cannot be filtered out, also cannot be detected. So the threat model we use is non-invasive attack. We can use antenna with a range of 1 to 7 meters. We can amplify the transmission power and trying to employ the direction of antennas for the signal injection for the longer distance. We also can use a portable EMI emitting system, such as the software-defined video, the devices. So you will see the EEG devices, that's brain control interface. And now is the antenna. So this is at least 1 meter away. Yeah. So we use the black box approach. So attacker know nothing about the machine learning, about the deep learning model, know nothing. Okay. The adversary cannot directly modify the data. Learning attack cannot. Okay. So our sightings focus on the machine learning task that's seer detection. They have 2 classifications, one seer, one non-seer. So we use the Brunner University dataset. They will have a lot of models. So logistic regression model, the SVM model, so decision trees. This is a traditional machine learning random forest. We also have the KN. We also have the deep learning based. So we use the CNN based deep learning model. So if there are no attack, all the models achieve F1 score is over 96. You will see, accuracy is high, it's very high. However, when they have attack, the accuracy is totally different. So you will see that is the first of all part is the EMI injected data. That's the theta wave band, 4 to 7 hertz. Then is original data. Then we put them together as a text signal, feed them to the machine learning model, feed them to. Then we do the detailed analysis. We found that the time and the frequency domain of the text signal being changing. So you see from here, there's no peak here, but you have a text signal with peak specific. Yeah. So here is the performance. You can see that if we use a sine wave and a square wave, they only affect this part. But if we have the theta, another one bring the band wave, so all of them, well, almost all of them is significant degree. So they make them the accuracy, is around the 20 something. They make all the machine learning model cannot be used. Also the tech, the effect could be 3 because later I will show that there's a lot of non-seer data being classified with seer. So that means if the patient don't have seer at all, but the system machine learning think they have seer, okay, the doctor may give wrong diagnosis. So this is the confusing matrix for different model when the EEG data is using EMI injector, bring wave band noise in the theta wave. So we use 4 to 7 hertz. Okay, so we found that we have a very interesting pattern. So a significant number of non-seer classified as seer. Okay, so we notice this. That means there's a vulnerability in the model's ability to actually distinguish, from seer and non-seer. Okay, that model is not robust to such kind of attack. So we conducted the first study on the non-invasive physical injection attack. We showed how the attack can degrade the performance of the machine learning model for the seer detection. We also highlight the need for the trustworthy bioelectronic signal based on measure processing and decision making to enhance the safety and reliability. That's our main message. So to mitigate such attack, we found that EMI attack. We already discussed to attack how to mitigate that. We found that a message, very small, tiny change in the sensor circuit can work. Okay, so this is published in ASCS. This is the paper. So in this one, the idea is very simple. So we just have, match dummy sensor here. It's called a transductor, circuits. You see this is sensor. This circuit is exactly almost the same as that. However, this circuit is insensitive to the measured, the signal, but it shares the same vulnerability with the sensor. It's the same. One example, just like temperature sensor, something like that. We change the sensing part, measuring the electrical material to resist. Okay, so what do we make? The malicious signal can affect the sensor and the TS circuit, but the legitimate signal cannot affect that. So we try to see analysis this first. If there is no tag, so this one is too close to 0, below the threshold. Okay, if we see the signal, the DT is bigger than the threshold, we see that there is attack. Then we compare the S prime T and DT. Then we know we can, mitigate that. Use the circuits to differentiate that. So that's the basic idea. This one is low cost, also very efficient. Also could be integrated in the view data, the sensor data, Okay, you see at the very beginning, it's very clear environment.
This is on the microphone. Then remove any data, no attack. Then we start attack from here. You can see we have sound wave, white noise injected. Then we compare examine the TS output. So compare it with the threshold, we can detect the attack. Then we use a simple circuit, we can medicate that. So it becomes true. There's no signal because it's a crowd area. Should be nothing for the microphone. Then we test it in the view, speaker system. That's Google Hello, Google system. So we, have the real data, is a high Google, what's the time is it? Then we have the malicious voice, hey Google turn on, hey Google turn down, all of this, okay? Then after use our method, then we crack all the malicious signal. You see all of them, hey Google what's time is, hey Google what's time, all of them. Okay, this is on the view system. Okay. So this means this method can recover the legitimate voice command. This means our system can work if there are the view, attack. Okay, at the same time, view time. So I would like to thank my collaboration and my students. The Dr. Lee from Ohio, Lee from the UPenn, Dr. Fu from the Northeastern, we moved, yeah, and Dr. Tan from UL, we have Sarah, Kevin from Florida. We also have other, the students and with the scholar. I also want to thank to the NSF, give me very generous support because they also gave me 5 answers for one already. So I'm really thankful to them. Okay, so this is the summary. I want to give the takeaways from this talk. First, the threat model and the computational of the CPS LT should not assume the ideal and imaginary feed world. Okay, it is an illusion. It's an illusion. Because in the real time, the attacker can use the side channel, can use the out-of-band signal to attack the system. So this one will break the assumption, will break your, ideal assumptions. Okay, so that could be the unexpected security, safety, and privacy risks. Okay. Also, I want to see that, as I said before, we have people seeing the EMR attack have a lot of limitation, but we really, in our real life, we can use EMI signal to steal the test account. Okay. Another one I want to share with you is their research direction to identify such attack, detect them, and correct them. Okay, you need to consider when you do this, you need to consider the physics of the sensor and the circuit and analog domain. Also, people seeing, oh, this is noise, this is not attack. This is not a correct idea. Because this is not the noise at all. As I said before, if you encrypt the data, if you have noise there, we still can work. Because attack can control the sensor, to what I want. But the noise, they usually, just give noise, they oscillate from, so you can see from this one, you see, we have a noise, right? In the situation, this always, this is already include noise there, yeah. So this is totally different. Then later on, I want to see, after you identify risk, you need to verify the security and availability. At this situation, you need a test bed, you need to protect CPS system for the education. So that's a test bed for the CPS security research and education. You can see that. So we also have a lot of demos in our YouTube channel. So you can scan the QR code. That will take you there. Okay. So thank you again for joining this talk. Now I'm happy to take questions.
Thank you. This was a lot of really interesting work. Looks like you all had a lot of fun doing it too.
Yes. No.
My question is, in the earlier part of your talk, the attack on the sensors, have you considered using, or is there a role for some flavor of machine learning or statistical technique either on the attack or on the defense? Because I don't think you didn't, maybe you don't need to use it, but maybe there's a role for it.
We didn't use that. We think our method, our program, always work. It already work. Right? But sometimes if you put a more machine learning there, the accuracy may be increase. But sometimes the machine learning maybe give you a little bit of error. Then we can precisely control it right now. Okay, machine learning give you a certain results. Sometimes in the extremity, extreme situation. Okay, so we also have a new paper. We use this 2023 paper, the set channel attack. We also use the traditional algorithm. But if you add in the machine learning method, accuracy will be much higher. We in that paper, we already can. So you are typing. I'm here. I have the mic there, microphone. Already, I can know what you are typing. Exactly, all of them. Yeah. Okay. So that one, if we are in this, I can show that to you. You see, with several rounds of the calculation, we really get detail because we have video there. You can see. At the first time, you didn't get the 80% of them. The later get 90%, and the later get 97%. The later get all of them. That's the mathematical algorithm. Okay, so that one I can show you. Okay, in some cases for the machine learning, you need to use machine learning. Some cases the solution already work. For the EMI, EEG data, we found that traditional machine learning works better than the machine learning, deep learning.
Yeah.
Some situation just like that, because the traditional one can really embed it on your cell phone, can run yourself, such as SVM, Vernal Forest can run very easy. Yeah. Okay.
Thank you.
We have a question online. The question is, since EEG waveforms carry some biometric markers unique to an individual during seizure and non-seizure states, how does injected signals confirm with expected signal morphology of that individual?
For the
So to confirm the expected signal morphology of that individual.
Okay.
You're gonna take a look.
I need to take a look. I cannot see this. Sorry. So EG covered by mark unique. Yes. So that's why we really, consider this because I consider it's a young situation. Okay, we have the, the corners, the EEG data set. We we process them very carefully because at the very beginning we found there's a lot of noise in there. Also, sometimes we found that given the patient, they have a lot of subjects. Different subjects, the machine learning, the traditional learning, they cannot, work for all. One cannot work for all. Yes, I think my students deal with this. We customize that. Even they really have one. Also, when we get the tag signal, I'm gonna move back. Okay. When we do the tag signal, we are very carefully here. Tag signal, actually we clean the data. We make the data have the same, the statistic, with the original one, because they have the amplitude, they have an energy level, different energy level. The conventional one, the previous one, that's the corners data set, we cannot access them. We are only create the attack signal. We do the same. The unit normalization. We make them similar, comparable. At least we need to make them comparable. If not comparable, so you see this one. There the power level is very small here. If this is very bigger, they just flash there, So we can process this. Okay. Yeah, I hope this can give you more details. Yeah.
Go ahead. This is sort of related to the ML attack, but I mean, it's not necessarily ML, but so a lot of these, they're attacks towards either a few set specific things, or you're optimizing towards specific objectives. Is there potentially some attacks that are more sort of broadband, and then you need to beat multiple sensors or sort of multiple different dimensions that you're attempting to attack? And then it seems maybe some sort of attack-based ML algorithm might be helpful to sort of navigate that gradient space. But yeah, that was something that when you mentioned that came up. Yeah.
So you either way combine the attack. You see, we use a laser, we use light, light, we use EMR, we use acoustic, we use magnetic, we put them together. Okay, you can attack the multiple sensors at the same time. You need multiple, sometimes because they have multi-modality sensor field, you can attack most of that. So at this situation is a little bit, complex because you need different settings. Okay, so specifically for different, attack, they have a different setting. So you need a bigger room to put all the settings together. Yes, we haven't tried that yet, but so that's why we see we need to test the bed. Yeah. So that's why my students, build the test bed.
I admit this came from trying to come up with how to use machine learning, not necessarily this would be the good idea. So it might not be the next best test. So like this sort of like how like it would help then maybe, but that might not be the best idea as you're saying, because you can in each individual domain you can use non-ML strategies and it breaks it. Yeah.
Some people, put the several sensor data, just like the car, several sensor data together, feed in the machine learning, right? Yep. But you can individually, attack, one of them. Then they have the integrity, you have inconsistency there. So the machine learning may give you wrong results. Yes, that's something really could happen. Because they do the integrity checking. But if you crash one of them, there is integrity constraints may not work. Okay.
Yeah, so for the first line of work, you did first of all very interesting work, the different types. Yeah. So for the first line of work, you use the sound, right? To modify.
Yes, that's a sound.
It's very interesting. You mentioned like one way to do it actually is you observe how the physical system works, and then infer information from that, and then use that knowledge to do the attack. I may miss that part. No, I'm sorry. What I'm trying to say is maybe you have already thought about this. What I'm trying to say is if you observe the physical system, the impact on physical system, right?
Yeah.
Because there will be, for example, delay, like the signal from the sensor to the actuator to the wheel. There will be delay, and also depending on the control, right? There are all sorts of control dynamics or mechanism. So how do you compensate for that in your I think framework?
It's really good question. The delay problem is really good question. You know that I said, these three parts need to work in parallel. We really have delay. Okay, but the delay time is short. My student told me, synchronize them. It's not easy. I think maybe the delay, some of them maybe is, less than 1 second. We observe that. This is really good. We really see the delay there. Yeah, but we, at the last, we compensate that. It does not affect much.
I'm thinking if you attack want to achieve certain goal, right? You want to do certain task, you want more accurate control.
Yeah.
Then that could be an issue because
but in our work we already observe delay. Yeah, we compensate the delay. Make it no problem. That's a real observation. Yes, if you really do the system, there's a delay there. Yeah, we see that. Also, in another paper, I can go back. I'm so sorry. I want to go back to the first one. I'm so sorry. That's too many slides here.
That's a really pretty much a slide here. So I want to go to here, the first part. We know we begin. So we go to the your presentation view around what is the beam. You see this paper? To process the audio, we really, do a lot of synchronization. From the first paper, we already started to synchronization. Okay, so this paper has a synchronization problem. This paper has a synchronization because you are typing. You don't know what's the first start. You start typing letter, or is in the middle of that. So you have to synchronize. So this one we also have a lot of synchronize. Okay, based on our observation, we try to align the dates together. So this one we need to do several rounds of we try to steal people's unconstrained key. So you type the passwords, you type anything, we can get that. So we really do that. We very beginning means 5 or 6 years before we already recognize this. Also this part, this part, see we have a synchronization. I think this part also have it. That's a detail. Really good question. Really problem. Yes, for the synchronization. Yeah. I do, the analytics. Yeah, we handle that. Thanks.
Oh yeah, thank you. Very nice talk. And my question is in that sound tech, have you measured how the distance and power impact your performance of the tech?
Yes.
Yeah, because I'm really curious about in some real world scenario, you cannot put your attack system very close to the target system.
Yes, that's a little limited. Yes. Okay, so such as if you do the EMI signal, not the EMI signal. And for EMI signal, we use the walkie-talkie. Okay, for the acoustic signal, we can hide some the microphone. Also for get the user key typing, we use a micro read just maybe under the under the table. Also, you can put a micro read in the ceiling. So that's can work. But so that's why we use ultrasonic. The video frequency is above the 27 kilohertz. So that makes some people cannot hear it. Some people can hear it. So cannot very close. If we you go our people, you can see some attacking distance is 10 meter away. Some attacking distance 1 meter away. Yeah. Some of them is 15 centimeter. None of them close. All of them is have distance. So this is really based on the device selection. So we give a rule on the device selection. That's a good question.
Right, Lamson speaker again.
Thanks, everybody.